And for section 2.4, we'll be looking at the precise definition of a limit, which will require us to construct some proofs called epsilon-delta proofs to demonstrate the closeness of a function to its limit L as the input variable x is sufficiently close to a. This is the look of the definition of a limit in the precise sense. This symbol is epsilon, the Greek symbol epsilon. It represents a very small positive quantity. Okay, demonstrating closeness here. Epsilon demonstrates the closeness between the output of the function f of x and the value of the limit L. And the Greek letter delta also represents a small distance, a closeness value, a very small positive number. And delta is used to represent the closeness of the input variable x to the value a. Recall that in general, we are not saying that x is actually going to get to a. Okay, and in general, we do not just plug a into the function. So L itself is not necessarily equal to f of a, for example. Let's unpack this definition here and see how we can interpret this first geometrically. Right, so we can put a picture to this. What is this definition telling us in the intuitive definition of the limit, as we've already seen with graphs of functions? Okay. And we'll try a few examples as well. Along with this lecture video here, you should have a worksheet. Okay, I've condensed the epsilon delta definition of the limit here. Given a positive epsilon, there exists a positive delta, such that if the distance between, we can interpret absolute value as distance, the distance or the difference between x and a is no greater than delta, right? Delta is positive. Okay. Then the difference or the distance between f of x, the output of the function, and the value of the limit L, that difference or that distance is no greater than epsilon. So how is this precise definition of a limit represented geometrically? Well, let's take a look at an example of a function whereby we know a limit exists. Here's the function, f of x is equal to x squared. And we're looking at, there's a point on this curve at 1, 1. It's a nice continuous function, nice and smooth. Okay, so a real easy limit. So we can say in sense of a limit, the limit as x approaches 1 of f of x equals x squared is equal to 1. Right? If we move along this curve from the left, we approach the y value of 1. If we move along this curve from the right, we also approach the y value of 1. Here's what we're saying precisely is what's happening. Epsilon is a choice of a number that is made to be as small as we wish, and we don't always know what epsilon is equal to. Okay, for some of these examples, we'll know epsilon. For this one, we're actually given a particular epsilon if we look at the graph closely enough. But in general, epsilon is allowed to be any number. And the idea is that it's like a game. If you challenge somebody to give you a number, a small number, and they gave you that small number, and you interpret it as, I need to get as close to the limit, okay, or closer to the limit than the number you give me. So epsilon is how close somebody is telling you to get to the limit as a challenge. Can you get this close to the limit? We then, because we don't have control over the output directly, we don't get to choose our y values here. We get to choose the x values. The way we play is by choosing x values that are sufficient for the function we're looking at, so that the result will guarantee that we are going to be as close or closer than the epsilon that was chosen for us. Okay? We want to be contained within a trap, a y value trap, a range of values, okay, where we will not wander any more than the distance epsilon away from the limiting value by selecting values of x within an interval around a. Remember that in general, we're not allowed to choose the actual value of a. We're trying to say how close how close to the value of a, so how close to 1 do we have to be in order to guarantee that the output y will be within the distance epsilon of the limit value 1. In this particular graph here, you can see that the value of epsilon that was chosen, the distance from the limit value, is 0.5. So it's as if this graph is suggesting to us that somebody challenged us by saying, you need to find the limit of this function as x approaches 1, okay, and you need to get the output plus or minus 0.5 within that margin of error, okay, of the actual limiting value. Okay, so we need to find out, based off of the output being allowed to be between now 0.5 and 1.5, because that puts us within a distance of 0.5 of the actual limit, what is the minimum possible x value, the smallest or the farthest to the left we could possibly be from a, and what is the farthest we could possibly be to the right, okay, of a as well. Now, each of those values, these two question marks here in this example, each of those values have their own distance from A. So there's, and delta is going to represent the best distance we can choose. So we can see from the graph here, it looks like this left bound here is farther from A, farther from 1, than the right bound is. So we have a delta for the left that is acceptable. This is how far to the left we're allowed to be. That is so that we choose, as long as we choose an x value that is between this line and this line, to plug into our function, it's going to bounce off the curve and it's going to end up somewhere between 0.5 and 1.5 in the output. So the distance between this question mark and the 1 is a delta to the left, and the distance between 1 and this question mark is a delta to the right. We want to choose the smaller of those two deltas, which then allows us to choose values of x that are sufficiently close to a that no matter which direction we look, we would end up between the outputs 0.5 and 1.5 in this case. All right, let's take another look at this using an animation within the textbook. Here they're giving us a nice smooth curve. It could be polynomial, it could be trigonometric wave. Okay, it's nice and smooth and continuous. Okay, the first thing we do is we choose a value of epsilon, or presumably someone has chosen an epsilon for us. Okay, and in general, we're going to want to do these proofs with the without knowing what epsilon actually is, so that we're prepared to find delta no matter what epsilon could have been selected. Okay? But it's okay now if we think about if there was already a small value epsilon that was chosen. Okay? Now, the value of the limit that we're going to be looking for is going to be represented by this point right here on the graph. Okay? So that the output of the function is going to be L, okay, at that point. That would be the actual value of the limit. But epsilon was chosen, and that means we are allowed to be within a distance of epsilon from L to say that we are, quote, close enough to the limit to say that it exists. And then what's going to happen is later is we're going to then choose another epsilon, a smaller epsilon. We're going to allow this region to shrink. We're going to get this, this trap right here, if you will. Okay, this interval on y, we're going to get it to be as small as we can possibly make it without letting it collapse all the way down to L. In other words, we don't want epsilon to equal 0. We want there to be a ceiling, and we want there to be a floor. And the limit itself is L. It actually exists. If no matter how small of an epsilon we select, if we can always choose an associated delta, that would give us a little interval around A that would have led to us being forced into that trap. So epsilon is chosen first, is the idea. And epsilon along with knowing the value of L, gives us an interval, a y value interval. This is represented in the precise definition in this statement, in this statement right here. If for every number epsilon greater than 0, saying that no matter what epsilon could have been chosen, as long as it is greater than 0, so let's assume this is a small number but positive. Where does epsilon go? The difference between f of x, which is the y value, the actual y value on the curve, and the value of the limit that we're going to be reaching. The difference between those in magnitude is less than epsilon. Let's unpack that statement a little bit further. This inequality right here symbolically. To say that the absolute value of f of x minus L is less than epsilon is to say that the difference between f of x and L is bounded between negative epsilon and positive epsilon. And then that means that f of x itself is bounded between, we can add L to everything now, L minus epsilon and L plus epsilon. All right, we've just unpacked that inequality there. This is represented then on the graph, okay, on the graph by saying, well, f of x, which is the actual y value from a point on the curve, and that varies, the y value on the curve will be no less than L minus epsilon and no more than L plus epsilon. And so suppose that this is actually where the limit value is L. Well, then L minus epsilon, since epsilon is positive, must be somewhere below L. And L plus epsilon, since epsilon is positive, must be somewhere above L. And this is symmetric, okay? This is symmetric about L because the same value of epsilon was chosen on both sides. That means that the actual output of the function, the actual y value, must be between this and this. And that's the trap that we've set in the graph like it shows in the book. Between L minus epsilon and L plus epsilon. Right? So this is an absolute value inequality. If you need a quick refresher on that, here's an example. If I have the absolute value of x minus 1 is less than 2, okay, that means that x minus 1 has to be between negative 2 and positive 2 on the number line. X minus 1 must be between these two quantities. Right? X minus 1 is between negative 2 and positive 2. And then you can add 1 to all of those, okay, and you get that negative 1 is less than x is less than 3, for instance. Right? If we chose negative 1 as the value of x and plugged it in here, we would get the absolute value of negative 2, which is 2, right? Which is a little bit too much. But if we chose something like negative 0.99, that's just a little bit more than negative 1, plug that in here, you'd get something like the absolute value of negative 1.99. And that would give us 1.99, which is less than 2. And on the other side, choose something just a little less than 3, like 2.99. Plug it in, subtract 1 from 2.99, you get 1.99. The absolute value of that is 1.99, which is just less than 2. All right? So when you have the absolute value of an expression, and it is less than a quantity, we can set it up as a compound inequality in this way. Okay? And we're going to have to do that in the x direction as well. Back to the animation. So what happens next? We say, well, if we're going to end up having to be between this lower bound here and this upper bound here, then let's take a look at the curve to see where those associated y values are and what x values they correspond to. We can see from our curve we would have reached this upper bound here, this y value, if we had selected this point on the curve. This is the point on the curve that has that y value that is the closest to the limit, right? We can see that there's another one out here, right, where the y value is also equal to that, but that one is not as close as this one is. And the idea is that when we're taking the limit, we're choosing x to be close to a, right? Sufficiently close to a. Okay, so we already know that x is going to be in a little neighborhood close to a. Okay. All right, so the y value, to reach this y value means, bounce off the curve, it means we must have hit this x value. And that x value right there, notice, for this curve, that x value is to the left of a. And if it's to the left of a, it's less than a. How much less than a? The amount less than a it's going to be, we're going to call that a delta. So we might call this delta 1, for instance, because this is some distance to the left of a, and the distance to the right of a isn't necessarily going to be the same delta. It depends on the curve. Right? It depends on the shape of the curve. Right? So, for example, suppose that I have an upper bound and a lower bound here, and then L which runs right down the center. Okay? It is possible to have a curve that gradually approaches L, but after it reaches it, maybe it steeply drags off, even if it's a continuous one. And in that case, then notice that we would have for the left edge, we would have a value out here, but for the right edge, we would have a value like right here. But the actual value that would reach the limit that would give us A is actually right here, which is much closer to the right edge than it is to the left edge. It's possible by the shape of the curve, right, that the delta that works on the left when finding this intersection is not the same as the delta that would have worked on the right when finding the associated intersection as well. Okay, it's possible for them to be different. It was not possible for this width and this width to be different because they are specifically chosen, these distances, to represent epsilon, which was the given value, presumably. So for every epsilon we're given, there will be associated with that 2 possible delta values. And of these 2 possible delta values, we're going to want to investigate which one of those 2 is the smaller of the 2. If there happen to be 2 different ones, that is. So in some examples, that'll be the same delta on both sides, but in some examples, they'll be different. And if they're different, we want to choose the smaller of the 2. Why? If we choose the smaller delta, okay, whatever the smaller delta is, will guarantee that we can only move that distance from A regardless of what direction, right? So suppose that to the right we had a smaller delta. If we choose the one to the right then as our delta, it tells us that we're never going to go farther than that same distance to the left. And that same distance to the left, given that it was a smaller delta, is certainly not going to exceed the actual boundary on the left. If, however, we took the larger of these 2 deltas and said that's the delta that we think is close enough, that would be problematic because the larger delta, if it were the one to the left, would be potentially too large if we used it on the right. And we have to allow ourselves to ultimately choose a delta that would work best on both sides of A. Let's take a look at the animation here and we'll work on some examples. Okay. Notice a change in epsilon may require a change in delta. We're going to change epsilon by making epsilon smaller. So we're shrinking down this trap over here on the y values. And the intersections with the curve at the upper and lower bounds result in different values of delta, right? Because this interval has shrunk as well. Okay. Now we have to be prepared for epsilon to be chosen to be any value. Let's put some numbers to this. Let's go to this example. I have that out here. Scroll down. There we are. Okay. Oh, similar example, right? We can go back. We can do this one, or I'll do that one next. Let's do this one. We were just talking about it. Find a number delta such that, okay, our goal is to find out what is the best delta we can find. Okay, the smallest delta that we can get, such that if the absolute value of x minus 1 less than delta, then the absolute value of x squared minus 1 less than 1/2. All right. Remember our precise definition of the limit. We are given epsilon greater than 0. Okay, we use that epsilon in the statement absolute value of f of x minus L is less than epsilon. Where is that statement in what we're given? It's this one right here, because this is f of x. Okay? This is f of x. So this is our statement. This statement right here says the absolute value of f of x minus L is less than epsilon. So, what is L? All right, we have that f of x already is x squared. What value of L are we given then? It would be this value, 1. And what value of epsilon have we been given? It would be this value. All right? It's 1/2. Okay? Okay, now, given epsilon is greater than 0, okay, there exists, or there is, a delta greater than 0, okay, such that the absolute value of x minus a is less than delta. Take a look at our statement here. What would be the value of, clearly x is x. What's the value of a? Okay, a is equal to 1. It happens to equal 1 also in this example, right? This is a right here. This is L right here. Okay? And what's the value of delta? That's what we're being asked to find. We want to find the value of delta. Now, what did we call this lower bound here? Okay, we said that this was going to be L minus epsilon. Isn't it, though? L is equal to 1, epsilon is 1/2, and 1 minus 1/2 is 0.5. And this value up here, well, that's L plus epsilon. Right? L plus epsilon, okay? I'll box our definition over here to kind of separate it a bit, all right? Right? 1 plus 1/2 would be 1.5. Now we trace the lower and upper bound here on this y interval. We trace it back to the graph, and we find there are 2 points of intersection, and each of those points are each of those points have an x value associated with them. We have an x value to the left of 1 and an x value to the right of 1. What would we call those? Well, if we're on the interval from x minus a, absolute value of x minus a is less than delta, that means that x minus a is bounded between negative delta and positive delta, which means that x is bounded between a minus delta and a plus delta. Which is the one to the left? Delta has to be a positive number, so a minus delta has to be less than 1. Okay? So that's what this one is then. This is our a minus delta right here. And this is a plus delta right here. Now, a is equal to 1, so this is 1 minus delta right here, and this is 1 plus delta right here. How can we find delta? We know the output. For instance, we know that the y value at this point is 0.5. We also know the function is y equals x squared. So 0.5 equals x squared. And we can solve for values of x. Okay? That's going to give us what this quantity is. Okay? In fact, I'm actually going to go a little further. I'm going to call this a minus delta 1. But I'm going to call this a plus delta 2. Because this distance and this distance don't have to necessarily be equal to each other. It depends on the symmetry of the curve. Okay. All right, so let's go and find delta 1. Okay, let's find delta 1. So to find delta 1, notice 1 minus delta 1 is, of course, the x value here, right? Okay. So we have that f of x is equal to x squared. We see that the output is 0.5, okay? And x is 1 minus delta 1. So 1 minus delta 1 squared is equal to 0.5. So with the square root property, we get plus or minus. All right, the square root is 0.5, or I'm going to go ahead and call that 1/2. Is equal to 1 minus delta 1 in general, right? Okay, and square root of 1/2 is root 2 over 2. Now, is it plus or minus? Well, look, we're close to this value. Because x is close to 1, this can be taken to be the positive of these two. Right? We can see from the graph here that it is, but remember, in a sense of a limit, as x approaches a, it means we must be close to a. So we expect to be close to a. So the negative root 2 over 2 would have been on the other side. Right? If we were looking over on the left side, when the input was -1, and there the output was 1, right? Okay? And if this was 1.5 and 0.5, if this were the limit we were investigating, that's the limit as x approaches -1, then what we would choose is we would choose negative root 2 over 2, okay, in order to locate one of our delta values, because that negative root 2 over 2 would have been closer to the value of a. All right. Good to keep in mind. Okay, so back to this. We now have an equation that we can solve for delta. Root 2 over 2 is equal to 1 minus delta 1. Okay, so delta 1 is equal to 1 minus root 2 over 2. Okay, so root 2 over 2 is approximately 0.7071. So this is approximately 1 minus root 2 over 2 is approximately 0.2929. Okay, so that would be the delta we would choose to the left. Okay, now find delta 2. Find delta 2. To find delta 2, we would take the 1 plus delta 2, which is our x value here, okay, and associate that with the y value 1.5 through the function f of x equals x squared. Okay, so again, if the output is 1.5, the input was 1 plus delta 2. So 1 plus delta 2 squared is equal to 1.5, or 3/2. So we take the square root, we get plus or minus, but again, because we can see from the graph here, we want the closer one to 1, so we're going to take only the positive root. Okay, so we have plus or minus the square root of 3/2 is equal to 1 plus delta 2, but we only take the positive of those roots. Okay, and rationalizing the denominator, this would be root 6 over 2. Okay, and then we can subtract 1 from that in order to get delta 2. Okay, so let's find out what that is. So root 6 over 2 is approximately 1.2247. So subtract 1 from that, and we get an approximation for delta 2, 0.2247. Okay, so that's approximately what delta 2 is. All right, so we have a delta 1 and we have a delta 2. Now our goal was to find delta, a single value delta, such that we can set it up this way. The absolute value of x minus 1 is less than delta all the time. That means of these two quantities, okay, what we want to choose delta to be the minimum of either delta 1 or delta 2. We want to choose the smaller of the two distances. Okay? And which one is the smaller of the two distances? Between these two, it would be this one, 0.2247. So choose delta is equal to 0.2247. Okay? So, in other words, what we're saying is, okay, geometrically, we're allowed to go to the right as far as 1.2247, which was actually this value right here, or we're allowing ourselves to go to the left, no more than a distance of 0.2247 to the left of 1. So 1 minus 0.2247 means we're going as far as 0.7753. Okay, so maybe about here. 0.7753. And so long as, okay, we're saying from the start, so long as we are no more than 0.2247 from A, as long as we are between these two boundaries, we're saying there's a guarantee that the resulting output, okay, is going to end up between 0.5 and 1.5. Right? In fact, it's going to do a little better than that on the lower bound because it's not even going to get close to 0.5. Okay. What the actual location of this, though, right here, right? Remember, this value right here was root 2 over 2. That was 0.7071. If we had selected the larger delta, that would have led us to there. If we had selected this delta 1, 0.2929, if we had selected that, it would have allowed for us to go 0.2929 to the right as well, which potentially could have pushed us outside of this range. 1.2929 would be out here, for example. Well, if this is 1.2247, then 1.2929 is to the right of that. And look what happens if we allowed ourselves to choose the delta on the left. It's setting up in a statement which actually lets the reader go to the left or the right by that distance. If the reader chose to go out that distance to the right, though, they would have gone up to the function and bounced off the curve, and they would have been outside of the trap. This is why it's important that we choose the smaller of the two deltas when we do this analysis. Now, this is an example of a continuous function, right? It was continuous at that point right there. The point was included. What about if there was a discontinuity? And that's what this example represents up here. So the limit here exists again, right? The limit for this function is this value right here. This is L. The limit is 2. And the value of A, that would be 3. Okay? So as x is getting close to 3, the y value is getting close to 2. Even though if you actually inputted 3 into the function, you're going to get this output here. So this point right here would be the point with the coordinates 3, comma, f of 3. Right? And that point exists off the curve. But the limit still exists. Right? The limit from the left and the limit from the right would each equal the value 2. Use the given graph of f to find a number delta such that if absolute value of x minus 3 is less than delta, delta has to be greater than 0, that's why this is over here, delta is always greater than 0, so is epsilon. Then the absolute value of f of x minus 2 is less than 0.5. We're not given what f of x equals here, okay, but we have enough information from the curve. Okay, so we're not given an actual function here symbolically. We're given its graph. But what we do know is that L is equal to 2 and epsilon is equal to 0.5. So this value is L, which is 2, plus 0.5, right? So this is our L plus epsilon, and this is our L minus epsilon right here. Well, then this value right here, 2.6, right, that is A minus delta 1, and this value, 3.8, that's A plus delta 2, and A is equal to 3, okay? So how far to the left are we? That's how we can find delta right now, okay? A minus delta 1 is equal to 2.6, but A is equal to 3, right? Okay, so the difference between these two is 0.4. So delta 1 is 0.4. That's how far to the left we're allowed to go. And to the right, what's the difference between these? That is the distance between these two values. That would be delta 2 is 0.8. What delta should we choose? Delta that we choose should be the minimum of our delta 1 and delta 2. that is the minimum of 0.4 and 0.8. Okay? And the minimum there would be 0.4. Okay? So if we choose delta to equal 0.4, if we choose delta to equal 0.4, then we're saying if, okay, then we're saying if the absolute value of x minus 3 is less than 0.4, okay, then as a result of that, the absolute value of f of x minus 2 is guaranteed to be less than 0.5. Unpack this statement, absolute value of x minus 3 is less than 0.4. That means that x minus 3 is between negative 0.4 and positive 0.4. That means that x is between 2.6 and 3.4, which we can see from the graph would be sufficient. So we're saying that by choosing 0.4, we're saying we're allowed to go as far to the left as 2.6, but we're also allowing ourselves to go as far to the right by symmetry as 3.4. As far to the right as 3.4, knowing full well that we'll still be safe if we go no farther than that. Okay? If we chose 0.8, that could have been problematic because that would allow for us to go as far as like 2.2. But if we went as far as 2.2, we would have not ended up in the range that we were hoping to end up in. Okay. Now from the worksheet, also there's a word problem in there. Let's try to dissect this one. A crystal growth furnace used to research right, to determine how best to manufacture crystals used in electronic components for the space shuttle. For proper growth of the crystal, the temperature must be controlled accurately by adjusting the input power. What do we control? We control the input power. Okay? W, the variable W, represents the power input in watts. Suppose the relationship is given by T of W, where T is the temperature, in degrees Celsius. Okay. Suppose it's given by this equation here, and this function, and this is a quadratic. Okay. So we are trying to control the temperature, which is the output of this function. But we're not actually controlling the temperature by choosing the temperature. We have independent control over the power in wattage. And by selecting the amount of power, that then leads through this function to an output of temperature. So we are controlling temperature through a dependency. Right? We actually have direct control over the power in wattage. Okay? So question A is, how much power is needed to maintain the temperature at 200 degrees Celsius? If we want it exactly 200 degrees Celsius, okay, it's asking us how much power would be needed. In other words, right, it's saying find W if T equals 200. Okay, so we go to the function for part A. Okay, and we set the output to 200. Okay. There it is. 200 is equal to 0.1 W squared plus 2.155 W plus 20. Okay. Now we have a quadratic here, right? We can, set this equal to 0, 0.1 W squared plus 2.155 W. Subtracting 200 from 20 gives us minus 180. We can solve this quadratic. Solving this quadratic, we're going to get two solutions, two values of W. Okay. Two values of W. Solve for W and determine which of those values of W is the more reasonable one, right, for the problem we're trying to solve right now. What value do you get for W? Okay? And you can round your answer to, let's say, 3 decimal places. So I get the values to 3 decimal places. W is approximately negative 54.548. But that's negative. It doesn't make sense for this exercise. So I'm not going to use that one. And W is approximately 32.998. So I'm going to take that one. So that's the number of watts of power in order to maintain the temperature at 200 degrees. B, if the temperature is allowed to vary from 200 degrees Celsius by up to plus or minus 1 degree Celsius, what range of wattage is allowed for the input power? So here's the idea. You wouldn't mind just a rough sketch here. The output we're trying to get is 200 degrees. Okay? And we're allowing ourselves to miss that mark by as much as 1 degree Celsius, either up or down. So we will go as high as 201 degrees and as low as 199 degrees. Now we know that the mark itself will be hit exactly, well, to 3 decimal places if we hit 32.998 watts. And the question is, how far to the left and how far to the right of 32.998 are we allowing ourselves to go? All right, so we want to find the value of x that would be associated with the lower mark of 199 and the value of x that is associated with the higher mark of 201. You find those two x values. So you find the distance between each of these x values here and the target value of 32.998. Okay, so that is, we want to solve the inequality that 199 is less than or equal to the temperature function, which is less than or equal to 201. Solve that for W. So we're going to get a W value on the left and a W value on the right. Okay. What values of W do you get? Right? Where the function T of W is this temperature function that was given right here. Okay. So you're solving for the input on the left boundary and the input on the right boundary. Let's take it to 3 decimal places again. All right, and so I've got 32.883 for the left and 33.112 for the right. So one on the left, one on the right. Okay. That is the range of wattage that would be allowed to 3 decimal places. Okay. Now, if we wanted to find the best value of delta, we should consider that A at the center, 32.998, we can find delta 1 and delta 2, which are the 2 distances. So delta 1 is this distance, and delta 2 is this distance right here, and we should choose the smaller of the 2. Okay? And that's part of part C. In terms of the epsilon-delta definition of the limit as x goes to a of f of x equals L, what is x? What is f of x? What is a? What is L? What value of epsilon is given? And what is the corresponding value of delta that we would want? Let's start with what is x? Okay, x is a variable, okay, a variable here, okay, and the value, the x represents, x is the power in watts. We're just using the variable w in place of x, right? What is f of x? That is the output. Well, f of x is called T of w here. So f of x is the temperature, okay, in degrees Celsius, okay, for the associated input of wattage. Okay. What is A? A is the value that we're trying to get the input X to get to. Okay? We would like to let the input equal to A if we could, if we had continuity. And the value of A right here is this quantity, 32.998. Okay? And that is, we can call that the target power in watts. Okay? And that value we found to 3 decimal places, 32.998 watts. Okay? What is L? The limiting value, okay, the target for the output. And that target is right here at the center here. It's 200 degrees, okay? So L is the target temperature in degrees Celsius, okay? And that was 200 degrees Celsius for us. What is the value of epsilon that is given? The given value of epsilon is 1 degree Celsius. That's how far above or below the target of 200 that we're allowing ourselves to go. Okay, so epsilon is 1 degree Celsius. What is the corresponding value of delta? Okay. To find out what delta is, we need the minimum of delta 1 and delta 2. Where delta 1, okay, delta 1 can be found as the distance, okay, I've noted it here, the distance from the left boundary to the A. So from 32.883 to 32.998. Okay, so it's the absolute value of 32.883 minus 32.998. Okay, so it's the absolute value of x minus a. And so that gives us 0.115. What is delta 2? Delta 2 is the distance from A to the right boundary. So what is delta 2? The magnitude of 33.112 minus 32.998. Okay? And that's going to be 0.114. So delta is going to be the minimum of 0.115 and 0.114. Okay, therefore we should choose delta to be 0.114 watts. So long as we are close to 32.998, close meaning no more than 0.114 in either direction, to the left or the right, we can expect that the resulting temperature will not go outside the range that we want. Okay, now let's apply this to a limit, okay, in general, okay, to prove a limit. It's a limit that we already know. Okay, let's take a limit that we already know how to evaluate algebraically and just apply the proof to it using this precise definition. Prove using epsilon-delta the limit as x goes to 4 of 2x minus 5 is equal to 3. Okay? The epsilon-delta, okay, given epsilon greater than 0, okay, there is delta greater than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, looking at our statement right here, let's find out what some of these quantities are. Okay. Let's start with what is, well, we know x is x. What about a? A is equal to x is approaching 4, so a is equal to 4, the fixed value. What is f of x? F of x is the function, right? This is the limit written this way, right? The limit as x approaches a of f of x equals L. Okay, so f of x would be 2x minus 5. What is L? L is equal to 3. So we have those three, right? We have a, we have f of x, and we have L. Now x is just going to be x. Okay, what is epsilon? In this case, we're not given an epsilon. We're supposed to write this in such a way so that no matter what epsilon was chosen, we would be able to find a delta that would be small enough. And in some cases, that means we need delta to be a function of epsilon. We might not find a constant delta. We might need to have delta as a function of epsilon. Okay, so epsilon can be any number. It's probably a small number. Any small number that is greater than 0. And delta depends on epsilon. That is, the delta we find now will be a function of epsilon. Okay? And we have to allow epsilon to be anything it wants to be. Start with the statement that the absolute value of f of x minus L is less than epsilon, where epsilon can be anything. Okay? And get from that a statement that says the absolute value of x minus a is less than some delta in terms of an epsilon. Okay? Here's the ingredients we have to work with. We're going to start with the absolute value of f of x minus L is less than epsilon. Now f of x was 2x minus 5. We're subtracting L, and the value of L was 3. Right? So we have the absolute value of 2x minus 5 minus 3. I guess I didn't need that parenthesis there. Minus 3. Okay? This is this statement, and that is less than epsilon, where epsilon can be any number. You're just saying that epsilon is greater than 0. That's already been stated, but we could also say that this is bounded on the other side by 0, because epsilon is to be greater than 0. And so does absolute value as well. Okay? So this is sufficiently small. And we want to get a statement that says the absolute value of x minus, what was a? A was 4. The absolute value of x minus 4 is less than some quantity. Okay, that's going to be a function of epsilon, and then that would be our delta. So let's transform this. Let's see. So look what happens if we do this. 2x minus 8, right? We can combine like terms, is less than epsilon. Okay. Now notice, what kind of a function is this right here? Y equals 2x minus 8 is linear. Okay, it's linear, and in fact, I'll go further than that. It's polynomial. What happens if you were to plug in 4 into this polynomial? Okay, 2 times 4 minus 8, right, is equal to 0. Now, if we can plug a number into a polynomial such that the output is equal to 0, right? P of 4 is equal to 0. Or 2x minus 8 is 2 times x minus 4. All right? Now we have the absolute value of this product. Well, the absolute value of 2 is just 2, so I can extract the 2 from here. And we have the absolute value of x minus 4 is less than epsilon. Now what we wanted was this, a statement that says the absolute value of x minus 4 is less than something, where that something is a function of epsilon, and we've got it now, because we can divide both sides of this by 2. The absolute value of x minus 4 is less than epsilon over 2. Therefore, epsilon over 2 is our delta function of epsilon. Okay? So we have found delta. Choose delta to be exactly half of epsilon. That is to say, in order to demonstrate that this limit will always be true, if someone were to come in and give us a value of epsilon. No matter what value of epsilon they choose for this example, no matter what value of epsilon they choose, we will want to choose exactly half of that value of epsilon as our delta. Okay? So our choice of delta depends on what epsilon we happen to be given. But we've written it in such a way where no matter what epsilon we are given, we know how to find the delta. We'll take half of epsilon, and that'll work for this particular example. Okay, so one more example here. A bit more complicated of an example to do abstractly like this. But after we just did a couple examples graphically, hopefully that visualization will help. The limit as x goes to 2 of x squared minus 3x plus 1, what's that equal to? We have the direct substitution property says we can just plug 2 in because this is polynomial. So 4 minus 6 plus 1, 5 minus 6 is negative 1. Okay? Prove the limit. Okay? Prove the limit, what I mean is using epsilon delta. Okay? So we have a limit as x approaches a of f of x is equal to L. Okay, let's list the ingredients we have here. Okay. First, a. Well, a is equal to 2. F of x. The function f of x is the polynomial x squared minus 3x plus 1. And the value of the limit L, well, that's equal to negative 1. Okay? We're going to want to start with, okay, get from the statement of the absolute value of f of x minus L is less than epsilon to a statement that says the absolute value of x minus a is less than delta, where delta is a function of epsilon in general, because epsilon is not specifically selected for us. All right. So let's start with this statement right here. The absolute value of f of x, well, f of x is this, x squared minus 3x plus 1, minus L, where L is negative 1. So f of x minus L, absolute value, and that is less than epsilon, where epsilon is greater than 0. Okay? But presumably small. Okay? Small, so that we are close to the limiting value, and therefore we're going to be close to the value of a as well in the x direction. Okay. All right, let's clean this up a bit. We've got x squared minus 3x plus 1 is plus 2. And then that is less than epsilon. What do we want? Okay, we want a statement that looks like this, where a is equal to 2. So we want a statement that looks like the absolute value of x minus 2 is less than some function of epsilon. That's what we want. Okay, let's see if we can get that now. Okay. Well, notice, if we plug 2 into this polynomial, what do we get? 2 squared minus 3 times 2 plus 2, well, that's 0. We have a polynomial will equal 0, right, when we input 2, so x minus 2 must be a factor of this polynomial. Okay, so x minus 2 is a factor, and you could find that this way, right? X minus 2 times what? X minus 1. That is less than epsilon. Okay, we've got our x minus 2, and it's in the absolute value, but we also have this x minus 1, and that's something that we need to deal with right now. And this is where it gets a little more complicated looking. Okay, we want to have the absolute value of x minus 2 to be less than delta, i.e., in other words, okay, we want, or we assume, or suppose, that x is very close to the value 2. We assume that x is already close to 2 by the time we get to this point. Okay? So, for example, let's choose a closeness that we are okay with. So, for example, if we choose that the absolute value of x minus 2 is less than 1. Why did I choose 1? Because it's sufficiently small. I could have chosen any number here. 1/2. You know, I want to choose a small number here and say, suppose that we are already close, I'll put that in quotes, close to 2. That is that we are not far. This statement right here, right, we're going to unpack this, and we're going to see how that's going to help us with this x minus 1 over here. This is just to say, suppose that, or assume that, x is already somehow close to 2. And that's what this statement is saying. Now, unpacking this statement to see what does that mean about x? Well, x minus 2 is bounded between -1 and +1. That means that x is between 1 and 3. Okay? Well, what does this assumption that we make here say about x minus 1? Because that's our other factor that we actually need a bound for. Well, this means that x minus 1, we could have found it from here by just adding 1, by the way, but x minus 1 is less than, so subtract 1 is less than 2, but greater than 0 for this particular example. By this assumption we made here, this assumption of closeness to 2, where we chose that closeness to be no more than 1, that resulted in the factor x minus 1, in this case being bounded between 0 and 2. This could have been a negative number, they could have been both in positive, whatever. But this means that for sure, okay, this guarantees, okay, so here I'll write in the notes, for sure, that means that the absolute value of x minus 1 is no more than the magnitude 2, because 2 is the higher of these. I mean, if the lower number was -1, but the higher number was 5, for instance, just throwing numbers out there, then the absolute value of x minus 1 would for sure be no more than 5. So you take the absolute value of both of these sides, and whichever one is larger, for sure the absolute value of the center is no more than that larger of the two. Okay? So now we have a bound for absolute value of x minus 1, under the assumption that we are sufficiently close to 2. Okay? Now, what does that mean then? How do we use that back in the original statement? Well, so now this statement right here, okay, let's see, x minus 2 times x minus 1 now, okay, is less than the absolute value of x minus 2 times the absolute value of x minus 1, okay? But that is less than the absolute value of x minus 2 times 2, because the absolute value of x minus 1 is no more than 2. And now we already said that this is no more than epsilon, so all of this is bounded above by epsilon. So we've taken this product and we said, well, this can be bounded by the absolute value of each one in a product, okay, a product of the two, and the absolute value of x minus 1 we already found an upper bound for, and that was 2, by our supposition here, that our assumption that this was going to be a 1. Okay, this 2 depended on us saying how close we say is close enough. Now then this gives us, all right, this gives us a statement that we can work with here. We have the absolute value of x minus 2 is therefore less than epsilon over 2, because we can divide both sides by 2. Okay. And even though I got epsilon over 2 down here, the same as I got up here, that wasn't really intended here, but that just happens to be the case for this example. Okay, so it's not like it's always epsilon over 2. Okay, it just happened to be the case here. But now here's how we choose delta. We actually have 2 deltas to choose from. Delta is the minimum of both of these deltas. What are the 2 deltas? Over here we made an assumption of the closeness. Either absolute value of x minus 2, let me just stand out a little more. Either the absolute value of x minus 2 is less than 1, or the absolute value of x minus 2 is less than epsilon over 2. Okay? So delta is equal to the minimum of 1 and epsilon over 2. Whichever one happens to be smaller, and that depends on the epsilon that is given to us, right? If epsilon was given to us to equal, 6, well then the smaller of these two would be the 1. But if epsilon was something like 0.1, well then epsilon over 2 would be the smaller one. Either way, this means when delta is chosen to be one of these two, then delta is the smaller of these two, then that means that the absolute value of x minus 2 is also going to be smaller than both of these. So the absolute value of x minus 2 ends up being smaller than 1 and epsilon over 2 as a result of choosing delta to be the smaller of these two. Okay, if it's smaller than one of them, then it must... if it's smaller than the smallest one, then it must be smaller than the larger of them as well. Okay? And in that case, then, our absolute value of f of x minus L, right, would look like this statement here, which written as this product here, would then allow for the absolute value of x minus 2 to be less than epsilon over 2, and the absolute value of x minus 1 would be less than 2. And epsilon over 2 times 2 would be epsilon. So this is going to work. This is a symbolic interpretation of what we were looking at earlier when we were dealing with the graphs, where it's easier when looking at these graphs when you already know the numbers. Okay, it gets trickier when they become more abstract. When epsilon can become any value and you have to find delta as a function of epsilon, it gets more challenging. Okay, all right, so that is enough for this section. So check out the homework and let me know if you have any questions on any of this content here. That would not be unusual to have questions on this or concerns on this type of content here. This is tough. These are proof exercises here. Okay. Good luck with the homework, and I'll talk to you later.